Hello students, I welcome you all to the online video lecture on course Heat Transfer. In the today's video lecture, we are going to derive the equation for LMTD, that is logarithmic mean temperature difference for a counterflow heat exchanger. In the first lecture, we have seen the LMTD for a parallel flow heat exchanger. In the today's lecture, we will see the LMTD of a counterflow heat exchanger. Let's read out the assumptions carefully. The first one, the first important assumption is, okay, the first important assumption is the overall heat transfer coefficient U is constant. The second is the flow conditions are steady. Third one is the specific heats and mass flow rate of both the fluids are constant. Fourth one, there is no heat loss to the surroundings due to the heat exchanger between, as the heat exchanger is being perfectly insulated. Fifth one, there is no change of phase of either of the fluid during the heat transfer. Sixth one, the changes in potential energy and kinetic energy are negligible. And seventh, last assumption is axial conduction along the tubes of heat exchanger is negligible. Okay, so I have explained in detail these seven assumptions in my first video lecture. So kindly go through the first video lecture on the derivation of LMTD of a parallel flow heat exchanger. Okay, so the link will be given in the description box. So let's go to the derivation on LMTD of a counterflow heat exchanger. Okay, so as we know that in counterflow heat exchanger, so this is the schematical representation or the flow arrangement of a counterflow heat exchanger in which the direction of hot fluid is opposite to that of direction of cold fluid. That means both hot fluid and cold fluid are moving in opposite direction. They are moving opposite direction. Okay. Now, how to draw the temperature distribution diagram or the temperature variation diagram along the length of the tube? Okay. Now, the topmost curve shows, this curve shows the hot fluid, the condition for hot fluid. So TH1 is the temperature or the inlet temperature of hot fluid, and TH2 is the outlet temperature of hot fluid. Similarly, this will be the inlet for the cold fluid and this is the outlet for the cold fluid, because both hot fluid and cold fluid are flowing in opposite direction. Hot fluid is from inlet to the outlet, and for the cold fluid we have inlet to the outlet. So that's why the temperature of hot fluid is gradually decreasing as it loses the heat to the cold fluid. Similarly, as the cold fluid absorbs the heat, so the temperature of cold fluid is gradually increasing from inlet to outlet. Now, this is a theta 1. Theta 1 is a difference between TH1 and TC2. That means theta 1 equals to TH1 minus TC2. Similarly, theta 2 is difference between these two temperatures. That is theta 2 equals to TH2 minus TC1. Okay. Now, for our analysis, we are considering a small elemental area, that is dA, and within that area we are considering the heat exchange process. Okay, now for this element TH and TC are the temperatures of hot fluid and cold fluid at that particular point, at that, I mean that at the element. Okay, now similarly differentiation of TH is the decrease in temperature within that element of the hot fluid, within that element of the hot fluid. Similarly, dTc is the differentiation of Tc. The differentiation of Tc is the increase in the differentiation of or the small increase in temperature of cold fluid within that element, and dA is the small elemental area, the area of small element. So this is the temperature distribution for a counterflow heat exchanger. Now let's proceed for the derivation. Let us consider a small elementary area dA of the heat exchanger. The rate of flow of heat through this elemental area is given by, okay, so as we have seen in the previous derivation, that is dq equals to u times ta into th minus tc, where u is the overall heat transfer coefficient, dA is the area of the small element, and th minus tc are the temperature difference within that element. So th minus tc can also be written as delta t. th minus tc can also be written as delta t. Okay, or you can take it as a theta as well. Okay, fine. In this case also, due to the heat transfer dq through the area dA, the hot fluid is cooled down by dth, whereas cold fluid is heated by dtc. The differentiation of tc, this will give the small increase in the temperature within that element, and dth is representing the small decrease in temperature of hot fluid within that element. Okay, now the rate of heat transfer dq within that element is given by minus time, this is very important, minus time m dot h cph into dh. So this is a very popular equation, q equals to mcp into dt. Okay, so why we are taking the minus sign here? See students, along the length of the tube, along the length of the heat exchanger, yes, the temperature is decreasing, that means it is losing the heat to the another fluid. If we consider from the thermodynamics point of view, if we consider this as a system, if we consider this as a system, then it is losing the heat, then it is losing the heat. So arbitrarily the sign convention is negative. Okay, so that's why we have taken minus sign here, minus m dot hcph into dh. I repeat, as the hot fluid is losing its heat to the another fluid, and if we consider hot fluid as a system, so from thermodynamics point of view, the heat lost by the system is arbitrarily considered as negative. So that's why we have taken minus sign here. So this is very important in the derivation, and this will be the turning point for your derivation. So please don't comment any mistake in this sign convention. Fine. Similarly, dq equals to minus m dot c cpc into dtc. So here also we have considered minus sign. Here also we have considered the minus sign. Okay, just a minute. Here also we are considering the minus sign, because if you see the length, as the length of the heat exchanger is increasing, the temperature of cold fluid is decreasing. Okay, so please try to understand this. So this is a direction of flow of cold fluid. Okay, this is a direction of flow of cold fluid, but along the length of the tube, if we see along the length of the tube, because this is a positive axis, this is a positive axis, and this is a negative axis, this is a positive axis and this is a negative axis. So we are considering the flow in, so this is a positive x-axis. If we consider this as a positive x-axis, yes, the temperature is decreasing gradually. The temperature of cold fluid is decreasing. Okay, though the direction of cold fluid is from right to left, it is increasing. But we are taking the sign convention along this direction. Along this direction. Okay, we can't take. See, for the hot fluid, we have taken in this direction. Okay, but for cold fluid also we have to take in this direction only. Okay, so for so as far as sign convention is considered, we have to take that the sign convention along the same direction for both hot fluid as well as the cold fluid, as we have seen in the parallel flow heat exchanger, as we have seen in the parallel flow heat exchanger. So this is the direction of heat flow. Okay, this is the direction of decrease in the temperature or the fluid flow. Okay, so cold fluid is from left to right. So for hot fluid, if we take the direction along the x-axis, the positive axis, the temperature of hot fluid is decreasing. So that's why we have taken minus sign for hot fluid. And similarly for cold fluid, if we take the direction of flow along the axis, the temperature of cold fluid is increasing. The temperature of cold fluid is increasing. So that's why we have taken the positive sign for cold fluid. The positive sign for cold fluid. Okay. Now, similarly here, so for both, we have taken the minus sign. I hope this is clear. This is a very important step while doing the derivation. Okay, so this will be the turning point for doing the derivation. Okay, now for a counter flow heat exchanger, so just to do the cross multiplication. So here he has mentioned in counter flow system, the temperatures of both the fluids decreases in the direction of heat exchanger length. So that's why we have taken the minus signs. Okay. Now do the cross multiplication. DTH equals to minus of dq divided by m dot h into cph. So just do the cross multiplication. So dth and dtc respectively are, so these are the denominator. Now the product of mass and specific heat, the product of mass and specific heat will give you heat capacity, okay, which is represented by the capital letter, capital C. So m dot h into small cph equals to ch. So ch is the heat capacity of hot fluid and cc is the heat capacity of cold fluid. Now let's take the difference between dth and dtc. So this is the similar way of doing the derivation as we have seen in the parallel flow heat exchanger. Okay, so you should be very careful while simplifying the things. Okay, so if we subtract, then this will be minus sign as it is. Okay, and this as we are subtracting minus into minus plus, it will become plus. So if you take the minus sign outside the bracket, you will get 1 by ch minus 1 by cc, because we have taken minus sign outside the bracket. This is a simple mathematics. Okay, now dth minus dtc is d theta. So because the difference between the temperature of hot fluid and cold fluid within that element is th minus tc. So difference we have considered as theta. So we have the differentiation sign here. So that's why we have to take d theta. Okay. Now we have to take the value of, or else you can say dq. So already we have written the equation for dq. So dq is given by uda into delta t, delta t, or th minus tc. So just take dq equals to this uda into th minus tc, 1 by ch minus 1 by cc as it is. Okay, the uda into theta as it is 1 by ch minus 1 by cc. So let's do the cross multiplication. D theta divided by theta minus equals to minus u times dA into 1 by ch minus 1 by cc. Now let's do the integration. So let's do this equation. Let's integrate this equation. So the integration from 1 to 2, that is theta 1 to theta 2, and here the integration is from 0 to a. So the minimum area is 0 at the inlet, at the immediate inlet the area is 0, and at the outlet we have the a as the area, total area is a. So we have to take the integration limits as 0 to a for this, 0 to a integration limit 0 to a for this. So let me write here, so here the integration limit is from theta 1 to theta 2, theta 1 to theta 2, and here the integration limits are from a equals to 0 to a equals to a. So these are the two integration limits. Fine, I hope this is clear. Now upon integration, you will get ln of theta 2 by theta 1, because upper integral is theta 2, lower integral is theta 1. Using the logarithmic property, log x minus log y equals to log x by y. Okay, so equals to minus u times a as it is. Okay, now the total heat transfer between the two fluids. This is very important equation. Q equals to Ch times, Ch is the heat capacity of hot fluid, which is the product of mass flow rate of hot fluid and the specific heat of hot fluid. Okay, so the product is Ch, and Th1 minus Th2. This is the total heat lost by the hot fluid. The total heat lost by hot fluid while flowing from inlet to outlet. Similarly, the total heat energy received by the total heat, or the rate of heat energy received by cold fluid is Q equals to Cc into Tc2 minus Tc1. Okay, So larger minus smaller, larger minus smaller. Okay. So let's do the cross multiplication. 1 by CH equals to TH1 minus TH2 divided by Q. Similarly, 1 by CC equals to TC2 minus TC1 divided by Q. Now let us substitute these two in this equation. So ln of theta 2 by theta 1 equals to minus UA into TH1 minus TH2 divided by Q minus TC2 minus TC1 divided by Q as it is. Okay. So we're supposed to take by bracket here. Okay, fine. So upon simplification, so Q is common term here. Let's take outside the bracket Q TH1 minus TC2. TH1 minus TC2 because we have to write this equation in terms of theta itself. Okay. So if you observe the temperature distribution diagram, so on the left hand side we have theta 1, which is a difference between TH1 minus TC2. So we have to arrange the equation such that we should get theta 1 and theta 2 in the final equation. Okay. So TH1 minus TC2 minus TH2 minus TH2 here as it is, because we have taken the minus sign outside the bracket. So TH2 minus TC1. Okay, minus TC1. I hope this is clear. So to avoid any confusion, we have to take the bracket here. So that will be more convenient for you. Upon opening the bracket, you will get a plus TC1. As we are taking minus sign outside the bracket, you will get minus here, minus TC1 as it is. Okay. Now minus UA by Q into the, instead of this difference, we can write theta 1 and here it is theta 2. Okay. Theta 1 and theta 2. So UA divided by Q into theta 1 minus theta 2, multiply with the minus sign, you will get UA by Q into theta 2 minus theta 1. So upon cross multiplication, you will get Q equals to UA into theta 2 minus theta 1 divided by ln of theta 2 by theta 1. Or this equation, this complete term is known as, this complete term is known as, this complete term, it is known as the logarithmic mean temperature difference, LMTD. So LMTD, it is also represented by theta suffix m, which is given by theta 2 minus theta 1 divided by ln of theta 2 by theta 1. Or else this equation can also be written as theta 1 minus theta 2 divided by ln of theta 1 by theta 2. Both are same. You can take theta 1 minus theta 2 and in the denominator theta 1 by theta 2, or theta 2 minus theta 1 in the numerator and in the denominator ln of theta 2 by theta 1. Okay, I hope this is clear. Now, so in special cases, in some cases, you may come across the situation where theta 1 is equals to theta 2. The temperature difference remains same as it is the counterflow heat exchanger. The temperature difference remains same. I mean to say that the temperature of hot fluid at the inlet is equals to temperature of the cold fluid at the outlet, because this is the outlet for cold fluid. This is the inlet for hot fluid. Similarly, TH2, sometimes the temperature of hot fluid at the outlet may be equal to, it may equal to the temperature of cold fluid at the inlet. It is in a very rare cases, it is in very rare cases. In such situation, you will get the theta 1 equals to theta 2 equals to theta, the temperature difference. Due to the equal temperature difference, you may encounter into the situation like theta 1 equals to theta 2 equals to theta. In that situation, theta 1 theta 2 both will get cancelled. In the numerator you will get 0, and here theta 1 and theta 2 both are theta only, so both will get cancelled. Ln of 1 equals to 0. So 0 by 0, it is indeterminate form. It is indeterminate form. For that we have to use the limits theory. You have to use the L'Hospital's rule. You have to use the L'Hospital's rule. For that, limits theta 1 tends to theta 1, theta 1 to theta 2 tends to theta 1. So theta 2 by minus theta 1 divided by ln of theta 2 by theta 1 as it is. Okay. So now take the theta 1 or theta 2 by theta 1, it tends to 1. Now take theta 1 outside the bracket. theta 1 outside the bracket, you will get theta 2 by theta 1 minus 1 as it is. Okay, now let theta 2 by theta 1 is equals to r. Let me consider this ratio as equal to r. So r tends to 1, r tends to 1 is theta as it is, because theta 1 is also equals to theta. So this ratio is r minus 1 as it is, and this theta 2 by theta 1 as r. Now, upon applying the L'Hospital's rule, that means we have to differentiate the numerator and denominator separately. So here the variable is r. Here the variable is r. Okay. So the differentiation of r minus 1 with respect to r is 1. Okay. Theta into 1 is the theta as it is. Now, differentiation of log of r with respect to r is 1 by r, 1 by r as it is, so which is equals to theta itself, because r tends to 1, the limit of r tends to 1. So hence theta 1 is equals to theta 2. So theta 1 equals to theta 2. So for that I can take only theta, only theta. Okay, fine. So theta m is LMTD for counterflow unit always greater than that of the parallel flow heat exchanger. So remember guys, the LMTD for counter flow heat exchanger is more than the LMTD of a parallel flow heat exchanger. Because of this reason, for the same size, the LMTD of counter flow, listen here carefully, for the same size of the parallel flow and counter flow heat exchanger, the LMTD of counterflow heat exchanger is more compared to the parallel flow heat exchanger. So that's why in most of the practical cases, in almost all industrial applications, like petrochemical industries, yes, wherever the chemical industries, wherever the heat exchangers are used, preferably counterflow heat exchangers are used, because it has a more effectiveness. For same size, the effectiveness of the heat exchanger is more for the counterflow as compared to that of the parallel flow heat exchanger. Okay, so fine. Now when the temperature variation of the fluid are relatively small, then the temperature variation curves approximately equals to straight line. So adequately the accurate results can be obtained by taking arithmetic mean temperature difference. So there is a difference between LMTD and AMTD. Okay, so if in practical conditions, if the temperature variation follows a linear relationship, say for example, this is the inlet and this is the outlet. So sometimes it will not follow the curved path, it will follow the straight line. It is a straight line. This is for the hot fluid and this is for the cold fluid, and this is for cold fluid. Okay, so this is a straight line. So in that condition, we have to use AMTD, that is arithmetic mean temperature difference. Arithmetic mean temperature difference, which is given by theta 1 plus theta 2 divided by 2. Theta 1 plus theta 2 divided by 2. Okay. So this is the brief introduction about the how to derive the equation for the LMTD of a counterflow heat exchangers. So if you have any doubt anywhere, you can put your comments in the comment box. Definitely I'll try my level best to resolve your doubts. Okay, so please don't forget to like the channel, share the channel and subscribe the channel, and don't forget to press the bell icon so that whenever I put a new video on YouTube, you'll get the notification instantly. Thank you and have a nice day.